Hello students, this is this section, Basic Concepts of Probability from the chapter Probability. This will be your introduction to the definitions, vocabulary, and formulas related to probability. The objectives for this unit are to be able to construct sample spaces, compute and interpret probabilities, approximate probabilities by using the empirical method, and approximate probabilities by using simulation. I would like to start with the definition of probability. The probability of an event is the proportion of times the event occurs in the long run as a probability experiment is repeated. And because of this, we need to also go over what's the definition of a probability experiment. A probability experiment is one which we do not know what any individual outcome will be, but we do know how long series of repetitions will come out. I know it sounds wordy, but some simple examples of a probability experiment could be rolling a die or flipping a coin. We do not know when we roll a die which side it will land on, but we do know it will be a side with a number between 1 to 6. Same thing with a coin. I do not know the exact outcome every single time I flip it, but I do know that it will be either heads or tails, although a student in class said that it could also be the edge. So I guess we have three options: heads, tails, or the edge. Now, we have a law that is called the law of large numbers that says that as a probability experiment is repeated, the proportion of times that a given event occurs will approach its actual probability. For example, when we're tossing a coin, let's say the first time you toss it, it lands on heads. Now, if we just use that observation as our probability, we have 100% chance that it lands on heads, given that it landed on heads. But if we keep on repeating that experiment, let's suppose now we have heads, and 1 tails as results of flipping a coin 3 times. Now we have 2/3, 2 out of 3 tosses being heads and 1 toss being tails. As you keep on increasing the number of times of the experiment, your outcomes, or the proportion of the outcomes, are going to be closer and closer to the probability of heads and tails. Because we only have 2 options when we toss a coin, the probability will be 1 out of 2 for each 1/2 or 0.5 or 50% chance in percentage form. This leads us to our following definitions, which is the difference between theoretical and experimental probability. Theoretical probability is based on reasoning without conducting an actual experiment. Think of just hypothetically speaking, if we toss a coin, what's the probability of it landing on heads or on tails? It's 50-50. 50% chance that it lands on heads, 50% chance that it lands on tails, based on the fact that we only have 2 options and each one of them is equally likely to happen. If we are using experimental probability, this will be based on observations. So let's suppose we take our previous example of tossing a coin. We had a 48 total right here of times this coin, hypothetically speaking, was tossed. Let's suppose that only this 12 times landed on heads. Now 12 out of 48 will be the probability, the observed probability of landing on heads, versus the other 36 times that it landed on tails. If we use these observations, then we're talking about experimental probability. If we use just the reasoning, it will be theoretical probability. A sample space contains all of the possible outcomes of a probability experiment. For example, the sample space for rolling a die 1 time will be 1, 2, 3, 4, 5, 6. The sample space for flipping a coin would be heads and tails. And the sample space for drawing a card from a deck of cards would be any of the 52 cards, assuming we're leaving the joker out of the sample space. It could be ace, it could be hearts, clubs, spades, and diamonds. Any of those. We have 52 cards in total. Now, every single outcome of a probability experiment, we're going to label event. We're going to call it an event. We're going to be using the function notation or a variation of the function notation to denote the probability of an event. For example, the probability of event A will be denoted with P of A. P, open parentheses, whatever's inside the parentheses, and then close the parentheses. Whatever's inside will be your event. For example, the probability of winning the lottery will be denoted as P of winning the lottery. Our formula for computing the probability of events in a sample space where equally likely outcomes will be the number of outcomes in A, or the number of ways you can have event A happening, divided by the number of possible outcomes in the sample space. Let's use K for the number of ways that you can have event A happening, and letter N to be all of the possible outcomes in your sample space. For the following examples, we're going to always assume that we're talking about a fair coin or a fair die, meaning that it's not tricked. We're going to assume that all of the outcomes in our sample spaces are equally likely. Now, I have my own version of this formula. Feel free to use the number of outcomes in A divided by the number of outcomes in the sample space, or the probability of favorable events divided by the total number of possible events. That's another way of seeing this formula. I like to rewrite it and think of it as what I want divided by what I can get, or whatever event you're looking for divided by anything you can get. I'm going to use the letters WIW and divided by WICG to abbreviate what I want divided by what I can get. But the number of outcomes of K and N will be the same. We're going to be using the exact same formula. It's just that we're going to label it different in these videos. Now, it's important to remember that the probability of an event is always between 0 and 1. Oh, I'm missing the T here. Sorry. The probability of A falls between 0 and 1, including 0 and 1. If something is certain to happen, then the probability of it is 1. If something cannot occur or is certain not happening, the probability of that event is 0. For our first example, let's compute the probability of an event. Suppose a fair die is rolled. We want to find the probability that an odd number will come up. Remember our formula for the probability. I'm going to denote this, the probability of an odd number coming up, just probability of odd. What I want divided by what I can get. What I want is an odd number out of my sample space that I denoted right here at the bottom. And how many ways can I get an odd number? Could be 1, could be 3, or could be 5. So I have the possibility of getting an odd number in 3 different ways out of how many possible ones? All of the possible outcomes in our sample space, 3 out of 6. Simplified form would be 1/2. In decimal form, it would be 0.5. And in percentage form, it would be 50% chance. Any form of these would be the probability of an odd number coming up when a fair die is rolled. Let's find the probability of a multiple of 3 coming up. What I want divided by what I can get. But let's use a notation. The probability of a multiple of 3. What I want divided by what I can get. And how many ways can I get a multiple of 3? It looks like only 3 and 6 are our possibilities. So 2 out of 6, which is 1/3, in simplified form, which is 0.33333 indefinitely, and in percentage form, it will be 33.33%. Any form of these. A number less than 5 comes up. I'm going to start showing you a different notation. Let's suppose X is the outcome of our dice, of die when we roll it. A number less than 5, that will be X is less than 5. Notice how it says strictly less than, which means it has to be 4 or 3 or 2 or 1. What I can get is any of the 6. My probability would be 4/6, which simplified is 2/3, which in decimal form is 0.666 indefinitely, which in percentage form is 66.66%. What's the probability that a number is greater than or equal to 3? Let's practice that notation. The probability that my outcome is greater than or equal to 3. This one is including that 3. We have anything equal to 3 or greater, which means our probability is again 4/6, which was simplified as 2/3, which in decimal form was 0.66666, which in percentage form was 66.66%. 67 if you round to the second decimal place, but it's 66 indefinitely. Let's take a look at this other second example. A section of an exam contains 4 true-false questions. A completed exam paper is selected at random and the 4 answers are recorded. We want to list all 16 possible outcomes in the sample space. We want to find the probability that all the answers are the same, assuming that all of the outcomes are equally likely, the probability that exactly one of the 4 answers is true, and the probability that 2 of the answers are true and 2 of the answers are false. We have to first start by listing all of our possible outcomes, which we're being told that it's 16. In other words, we're finding the sample space. I'm going to show you how to construct a sample space tree. How many options do we have for the first question? We have 2 options. My first question or my first answer could be either true or false. For my second question, that's for my first question. For my second question, given that the first one was true, I have 2 options. The second question can be true or the second question can be false. Same thing, if my first question was false, my second question could be true or my second question could be false. This is because we were assuming that all of the outcomes are equally likely to happen. For my third question, given that the first question was true and the second question was true, we have 2 options, true or false. For my third question, given that the first one was true and the second one was false, again, we have 2 options, true or false. If the first question was false, the second question was true, I have again 2 options for the third question. And if both of my first and second answers were false, I still have the option of having true or false for the third question. Finally, for our fourth question, we have now true, false. I'm going to stop drawing the arrows, just put the little lines. True, false, true, false. This is my tree of possibilities. And to construct each one of your possibilities, you're going to follow the arrows or the branches. The first option would be true, 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 true. All of our answers being true. Then our second possibility would be true, 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 false. True, 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 false. Then we have our third possibility being true, true, true. We're already done with the third one being true. False, false, true. True, true, false, true. Or true, true, false, false. True, true, false, false. And then I'm done with my second question being true. Let's look at the ones that are for the second question being false. True, false, true, true. I'm just gonna follow the branches for every single possibility. True, false, true, true. And the sixth possibility. True, false, true, false. And you keep on doing that, going for every single option on this last branches. For all of these are different outcomes. Of course, you don't have to draw a tree diagram. If you wanted, you can just go ahead and start brainstorming all of your possible outcomes. The problem is that if you don't know what's the total, you could miss some. And if you're not careful enough, you could repeat some too. Here are the 16 outcomes in my sample space for 4 true-false questions. I want to find the probability of having all of the answers being the same. In how many ways can that happen? Either all of my answers are true or all of my answers are false. What I want divided by what I can get. What I want can only happen in 2 ways out of how many possible outcomes? 16 in total, which is 1/8, which in decimal form, 0.125 or 12.5%. Any of these will be your answer. Assume the outcomes are equally likely. Find the probability that exactly one of the 4 answers is true. Let's find how many ways can that happen. We have exactly one of them, false, true, false, 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 true, false. This one right here. False, 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 true. Am I missing one? Yes, this one. True, false, false, false. Looks like all of these are my possibilities. So 4 out of 16. What I want divided by what I can get, which in simplest form is 1/4. Decimal form will be 0.25. Percentage form will be 25%. Find the probability that 2 of the answers are true and 2 of the answers are false. I have true, true, false, false, true, false, true, false, true, false, false, true, false, true, true, false, false, true, false, true, false, false, true, true, and it looks like that's it. Which is 1, 2, 3, 4, 5, 6. 6 out of 16. 3/8. Let's practice creating sample spaces for different scenarios. Let's start with creating the sample space for flipping a coin and rolling a die. How many options do I have for flipping the coin? 2, heads or tails. How many options do I have for rolling a die? Given that the coin landed on heads, I have 6 options for rolling a 6-sided die. Given that your coin landed on tails, you also have 6 options. Heads once, and then heads 2, heads 3, and so on. So my sample space, which we're going to denote here in roster notation form, will be H1, H2, H3 for heads 3, all the way to heads 6. And for tails, tails 1, tails 2, tails 3, all the way to tail 6. Our sample space has 12 possible outcomes. Let's create a sample space for having 3 puppies, and we mean like sex, whether it's a female or a male. How many options do we have for the first puppy? It could be a female or a male. That's for the first puppy. For the second puppy, how many options do I have? Given that the first one was a female, I have again female or male for the second puppy. And if the first one was a male, it can be again female or male. Finally, for our third puppy, we have female or male, given that the first 2 were females, or female or male if you have the first one being a female, the second one being a male, or female and male for the third puppy if the first one was a male and the second one was a female, or female male if the first one and second one were both males. Now let's follow the branches to create our sample space. Female, 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 meaning all 3 puppies were females. Female, female, male. And the third one, female, male, female, female, male, 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 female, female, male, female, male, 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 female, and male, male, male. We have a total of 8 possible scenarios or possible outcomes when we're having 3 puppies. Now, remember, we are using these 3 diagrams to calculate probability. If they ask you what's the probability that all of my puppies were females, that can only happen in one way: female, female, female. So the probability of having 3 females is 1 out of 8. The probability of having only 1 male, we have 1, 2, 3 different scenarios when one of the puppies is a male and the other 2 are females. You don't have to construct a tree diagram every time, but it will certainly help to find your sample space without having to brainstorm or struggle finding all the possible outcomes. Let's look at 2 more examples of finding sample space. Let's find a sample space for flipping 2 coins. We have heads or tails for the first coin. And if the first one landed on heads, we have heads and tails. If the first one landed on tails, we also have heads or tails for the second one. Looks like we have heads, 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 tails, tails, heads, and tails, tails. We only have 4 possible outcomes when we toss 2 coins. Now let's talk about the sample space of rolling 2 dice. This one's a little bit big because for whenever you toss your first die, assuming the first one landed on a 1, we have 6 options for the second die. For the first die landing on 2, we have also 6 options. All right, here is the sample space for rolling 2 dice. If you notice, we have a total of 36 possible outcomes. Let's suppose we want to find the probability of rolling a sum of 7. And how many ways can we have a sum of 7? Well, 5 plus 2, 6 plus 1, 4 plus 3, 3 plus 4, 2 plus 5, and 1 plus 6. It looks like we have 1, 2, 3, 4, 5, 6 out of 36 options. And of course, you will have to simplify after finding 6 out of 36, which is 1/6. Let's suppose we want to find the probability of rolling a sum less than 5. And this is a trick one. Less than 5 does not include the numbers that add up to 5. So no 4 plus 1, no 3 plus 2, no 2 plus 3, no 1 plus 4. Only these options: 1 plus 1, 1 plus 2, 2 plus 1, 3 plus 1, 2 plus 2, and 1 plus 3. 6 out of 36 again. Now let's suppose I want to find the probability of rolling a sum greater than 8. In how many ways can you get a sum greater than 8? Greater than, strictly greater. 4 plus 5, 4 plus 6, 5 plus 4, 3 plus 6, 6 plus 3. All of these will give me a sum greater than 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 36. If we want to find the probability of not rolling a pair, meaning not rolling a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, we're going to exclude these 6 possibilities out of the sample space, and it will be everything else that is not a pair. So 30 out of 36. Rolling at least 1 3. So both of the dice being 3 or one of the dice being 3. It looks like any of these, which are the 3s on the first die, and any of these, which are the 3 on the second die. You have to count them and divide by 36. Rolling a sum of 15. What if we want to find the probability of rolling a sum of 15? Our greatest sum is 12. It's not possible. What's the probability what something's not possible or cannot happen? It would be 0. Unusual events. We call unusual event an event that has a very small probability. Sometimes we want to use the cutoff of 5% to consider an event being unusual. In the case they give you a different cutoff value, use that cutoff value. But unless specified otherwise, we would like to use 5%. The empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. Let's take a look at example 3. The General Social Survey asked 46,349 women how many children they had. The results were as follow in the table. Let's answer the following questions. What's the probability that a sampled woman has exactly 2 children? If we look at our information, we have a frequency distribution with a single value for our classes. We have an open class at the very end, and our count or frequency will be on the right. What's the probability that a sample woman has exactly 2 children? How many women said they had 2 children? What I want divided by what I can get. I want any of those 11,290 women, but I can get any of the 46,349. I got 0.2435 rounding to the 4th decimal, which in percentage form will be 24.35%. What's the probability that a sample woman has fewer than 3 children? In this example, we have to add multiple classes, the frequency for multiple classes. Because it says fewer than, it means less than 3. We're not going to include 3. We're going to add how many women said 2 or 1 or 0. How many women said that they have 2 or 1 or 0 kids? And divide by the total. If I round to the 4th decimal, this will be 0.6771, which in percentage form is 67.71%. Now, assuming that this is a simple random sample of women in the United States, we want to use the empirical method to estimate the probability that a U.S. woman has more than 5 children. This is just a sample of 46,349 women. We're going to use the probability of these women to approximate or estimate the probability for any women in the U.S. having more than 5 children. Again, just like in the previous slide, we're going to have to add how many women said 5 plus 6 plus 7. But notice, it says more than 5 women. I'm going to exclude 5. It's just going to be whoever has 6, 7, 8, or more children. I got that my probability was 0.0478, which in percentage form will be 4.78%. Let's go over one more question using this data. We want to use the cutoff of 5%, and we want to find if it's unusual for a woman to have no children. We have to find the probability of a woman having no children in this data set and evaluate or compare it to 5%. If it's smaller than 5%, it's unusual. If it's greater than 5%, it's not unusual, or it's just usual. What I want divided by what I can get, 12,656 divided by 46,349. Which have the number of women that had 0 kids and our total number of women that were surveyed. 27.31%. Given that it's greater than 5% and greater than a fourth of the women that were surveyed, I would say that it's not unusual for a woman to have no children. For example 4, I would like you to challenge yourselves. I want you to pause the video when you read the question, or when I read to you the question, and I want you to practice finding the answer by yourself. Then you can just let the video go and I'll show you how to do it, how to find each of the answers. According to the Agency for Healthcare Research and Quality, there were 409,706 hospital visits for asthma-related illnesses in a recent year. Here we will find the age distribution, which is a frequency distribution. If you notice on the left, we have our classes, which denote the age ranges. And on the right, we have our frequency for each class, which are the number of visits for between those ages. Our first question is, what's the probability that an asthma patient is between 18 and 44 years old? We had a total of 79,659 visits for asthma-related illnesses between the ages 18 and 44. What I want divided by what I can get. What I want is one patient out of those 79,000 divided by what I can get, and I can get any of those 409,000 patients. I got 19.44%. What is the probability that an asthma patient is 65 years or older? We have to add some of our frequency for different classes. 65 or older will be the class of 65 and 84. And 85 and up. I have to add those two and divide by our total. I got 0.2378, which is 23.78. We're going to be using the cutoff of 5%, and we want to find if it's unusual for an asthma patient to be less than 1 year old. We only had 7,866 visits for patients younger than 1 year old. I'm going to divide 7,866 by our total number of visits. I got 0.0192, which is 1.92%. Using the cutoff of 5%, we're going to be saying that yes, it was unusual to have a patient younger than 1 year old.